If you've loved the latest James Webb space images, you need to see what I'm about to show you. ESA's Euclid Space Telescope has sent back its first batch of images, and they're some of the best space pictures I've ever seen. Known as Euclid's first light, this photo collection is a dazzling tour of the universe's galaxies, and scientists are absolutely thrilled by what they're seeing. Euclid's photos challenge our ideas about how the universe evolved, offer fresh insights into the role of dark matter in shaping the cosmos, and even let us peer into the past by capturing galaxies 10 billion light-years away. Plus, the photos themselves are stunning. On July 1st, 2023, the European Space Agency launched the Euclid telescope from Cape Canaveral, Florida. After traveling about 1.5 million kilometers, it joined its siblings, the Gaia and James Webb telescopes, in orbit around Lagrange Point 2. This location is ideal for studying and imaging deep space because it allows telescopes to keep the Sun, Moon, and Earth behind them at all times, so they never interfere with observations. It's also close enough to Earth to make communication easy. Since L2 keeps pace with Earth's orbit around the Sun, we stay close to our instruments. Euclid's 6-year mission is designed to explore the composition and evolution of the universe. It will do this by building the largest and highest quality 3D map of the cosmos ever made. In October 2024, Euclid started sending back the first pieces of this map. I'll show them to you shortly. As Euclid continues to scan the sky over the coming years, scientists hope the new data will help them understand the role of gravity and dark matter in the structure and expansion of our universe. How it works first, you need to understand 3 key things that make this telescope and its pictures so unique. Firstly, Euclid's ultra-wide lens captures more of the sky at once than any telescope ever has. It gathers high-resolution light data from billions of galaxies, some as far as 10 billion light-years away. Compared to ground-based surveys, it has 4 times the resolution and 15 times the sensitivity in the near-infrared. It can also spot objects hundreds of times fainter than the ones Gaia can detect. In a single observation, Euclid records vast cosmic structures and precise details of individual galaxies. The result? An image that conveys multiple cosmic scales at the same time. Secondly, Euclid measures subtle distortions in galaxy shapes caused by dark matter's gravitational influence, creating a gravitational lensing map. This is key to understanding how galaxy clusters grow and evolve, while also showing us how dark matter has played a role in literally shaping the universe. Finally, Euclid is creating a 3D map of the universe with 2 advanced instruments. The Visible Imaging System, VIS, captures ultra-sharp images in visible light to measure galaxy shapes and positions, while the Near-Infrared Spectrometer and Photometer, NISP, measures redshifts, placing galaxies in 3-dimensional space. Euclid is kind of a big deal. The excitement in the astronomical community about these images is real, as summed up by one Euclid project scientist. So let me take you on a tour through Euclid's first light images one by one, starting with our map. Thanks to ESA's Gaia and Planck missions, we already have a solid map of our Milky Way. Euclid is tasked with gathering data on the dark parts of that map. So far, it has covered about 1% of the map it was sent to create. Between March 25th and April 8th, 2024, Euclid took 260 pictures of the southern sky, covering an area 500 times the size of the full moon we see from Earth. Putting these pictures together, scientists created a mosaic spanning millions of stars and galaxies. And remember, this is just 1% of what it's planning to do. Because Euclid captures both big picture and detailed data at the same time, researchers can see the sky at different scales. From extragalactic views, we can zoom into galaxy clusters, their cores, and even individual galaxies. So let's explore some of these cosmic structures, starting with one of the biggest known in the universe. This is the Perseus cluster, located 240 million light-years from Earth. This image shows over 1,000 Perseus cluster galaxies and more than 100,000 faraway galaxies in the background. Scientists think the way galaxies are organized can tell us a lot about the distribution of dark matter and dark energy. You see, gravity might cause dark matter to organize itself into filaments. We aren't sure, but NASA scientists believe it's possible that where these filaments intersect, galaxies stick closer together, forming a cluster. The theory goes that if there were no dark matter, galaxies would be distributed evenly throughout the universe, which obviously isn't the case. While many galaxies in the Perseus cluster are already known, cosmological simulations predict there should be several dwarf galaxies there too. If we could see those faint galaxies, we could analyze their shape and distortion relative to the cluster and background to determine how dark matter is distributed. The problem is, these dwarf galaxies tend to be overshadowed by older stars shining infrared light, so they've evaded direct observation until now. Euclid discovered more than 630 previously unknown dwarf galaxies, which is a huge breakthrough in the study of dark matter. Let's go to our next destination. Say hello to irregular galaxy NG C6822, shining bright 1.6 million light-years away. It was first identified as a remote stellar system by Edwin Hubble in 1925. Now, almost 100 years later, Euclid is sending back high-resolution images of the entire galaxy and its surroundings. The JWST also imaged this galaxy a few years ago, but with a much narrower field of view. Scientists are interested in Euclid's wide-angle photos of this galaxy for what they might tell us about star formation and the early universe. You see, stars smash lighter atoms like hydrogen and helium together to produce heavier atoms, including metals. This process happens across a star's lifespan, which is why we don't see many heavier elements in the early universe, because they take time to accumulate. Surprisingly, many of the stars in NGC 6822 have very low levels of metal atoms. By studying low metallicity galaxies like this one, scientists hope to learn more about how galaxies evolved in the early universe. Euclid has made that a monumentally easier task thanks to the color information from its NISP instrument and its wide field of view. Speaking of globular clusters, here's one in a different part of the sky. Globular cluster NGC6397 is 7,800 light-years from home, making it the second closest one to us. Globular clusters are kind of like Hollywood, a high concentration of stars in one place where everyone is trying to outshine everyone else. What does this mean? The smaller, dimmer stars get drowned out by the bigger, brighter ones. On top of that, they extend quite a long way out from their center, with the radial parts mainly made up of low-mass, faint stars that, until now, have been hard to see. Ironically, it is these faint stars that hold the most scientific interest for unlocking the history of the Milky Way. As Davide Massadri of the National Institute for Astrophysics in Italy puts it, currently no other telescope than Euclid can observe the entire globular cluster and at the same time distinguish its faint stellar members in the outer regions from other cosmic sources. Hubble actually imaged the center of this cluster in 2021, but to image the entire cluster, including the sprawling outskirts like Euclid did, would have taken it far too much time and resources. On the other hand, Euclid snapped this shot in just 1 hour, and it is absolutely beautiful, both aesthetically and scientifically. Caldwell 5, commonly referred to as the hidden galaxy, earns its name from how elusive it is. Although it's located about 11 million light-years away, spotting it isn't easy. It lies directly in the crowded plane of the Milky Way. Dust, gas, and foreground stars obscure our view, making it difficult to observe from Earth. What makes Caldwell 5 especially fascinating is its resemblance to the Milky Way. Because we live inside our own galaxy, we can only see it from one fixed perspective. But Caldwell 5 gives astronomers a rare outside-in look at something that might behave similarly to our own galactic home. Thanks to Euclid's powerful near-infrared vision, scientists were able to pierce through all the visual noise and capture this galaxy in remarkable clarity. While ground-based telescopes have imaged it before, they've never revealed this level of detail. Leslie Hunt from the Euclid Consortium explains, the image might appear ordinary, like something any decent telescope could take. But that's misleading. What's remarkable is that Euclid gives us a wide-field image of the entire galaxy and lets us zoom in close enough to identify individual stars and stellar clusters. This allows us to trace star formation over time and study how stars were born and evolved throughout the galaxy's life. Despite all we've learned, mysteries remain. Scientists still don't fully understand how spiral galaxies maintain their elegant shapes or the exact role dark matter plays in building and sustaining them. Now, Euclid's crisp imaging, showing Caldwell 5's spiraling arms and wispy dust lanes, could help unlock answers about how stars, gas, and dust interact on a grand scale in galaxies like ours. And finally, we arrive at the last stop on our cosmic journey, the magnificent Horsehead Nebula. This celestial formation has been photographed countless times before, but never quite like this. Euclid's 1-hour exposure produced a razor-sharp, ultra-wide image that reveals never-before-seen intricacies. It's like someone casually took a snapshot at a scenic overlook, except it's 1,375 light-years away. The Horsehead Nebula is part of the vast Orion molecular cloud complex. It sits just below Alnitak, the easternmost star in Orion's belt, and it marks one of the closest massive star-forming regions to Earth. What makes this region scientifically exciting is the potential discovery of previously undetected Jupiter-sized planets. One such planet, known as S Auri 62, has already been found here. It's roughly 10 times the mass of Jupiter and scorches at a temperature of 1,200 degrees Celsius. The glow behind the nebula comes from ultraviolet light radiating from Sigma Orionis, a nearby star. The Horsehead itself, however, is made of cold molecular hydrogen, which emits almost no heat or visible light, making it a perfect place to study star formation in its darkest, quietest stages. Researchers are especially interested in the Sigma Orionis region. It's home to an open star cluster that may contain many free-floating planets, worlds not bound to any star. Thanks to Euclid's extraordinary sensitivity, scientists have now detected a much larger number of smaller FFPs than ever before. And this is only the beginning. Euclid still has 5.5 more years of mission time left. The data it collects will reshape our understanding of the universe, from how stars and galaxies form to the invisible forces of dark matter and dark energy that shape everything. Someday, Euclid's 3D map of dark matter might lead to breakthroughs in fundamental physics itself. Until then, we get to enjoy more breathtaking images as they continue to arrive. Thanks for watching.